Okay, class. Notes for 3:30. Chapter 10. Right, moving on. Antennas is behind us. Right. If you haven't finished homework for the antenna stuff, go ahead and do so, and then send me an email that indicates that you've done that. Right. Let's keep up here. Keep pushing on this. So this new chapter, right, is on microwaves. We time permitting, we'll go back and pick up chapter 9 on electromagnetic compatibility. But for now, we're going to move ahead to chapter 10 on microwave engineering, right? So, and we'll follow the text pretty closely here. We'll follow Stu's presentation uh, pretty carefully. And so, first order of business, right, is to start reading in this chapter and to get a grasp on some of the general concepts, right? That first introductory section there on page 541 and 542 is good reading. Go ahead and do that, and that'll just kind of set the background for why we're studying the things that we're studying, right? So, right, the first section in here is on microstrip, right? So we kind of looked at microstrip when we talked about microstrip patch antennas, right? But we didn't really discuss necessarily how to uh, get a desired characteristic impedance by adjusting the width, the height ratio uh, for the microstrip, right? So we need to address that. And to lost my pencil. Okay, there it is. Right. So, right, read the intro. Right, study that figure 10.1. Again, figure 10.1 is just typical transceiver. Right. So study this diagram. Pretty much straightforward. Signal comes through the antenna, goes through the duplex filter. Right. First order of business is a low noise amplifier. Right. Out of the amplifier goes a bandpass filter. Right? Cuts out any signals, extraneous signals other than the one at the desired frequency. Low noise amplifier, the signal coming in from the, the distant source is weak, and so the first thing that needs to happen is it needs to be amplified. Right? Bandpass filter. Then you typically, but not always, mix that with a local oscillator, right? What is the reason for that, right? Well, this gives you a product of two frequencies, the incoming frequency and the local oscillator frequency. And so you'll get a sum and difference frequency. The difference frequency is lower than the carrier frequency, but has all the same information on it, right? So by lowering the frequency, it makes the design of the amplifier, the IF amplifier, the lower frequency amplifier, easier, right? So once it's converted down, you can go to digital from the analog signal with an A to D converter, and then that information, right, the bits are pulled off of that carrier, processed in some way. That's how you get the information off, and might be voice, it might be data, who knows, right? So on the other direction, right, uh, you take the information and you uh, pass it through a digital to analog converter, right? So you modulate, and then you up convert, again, bandpass filter to get rid of any extraneous signals, preamp, power amp, and then out of the antenna. So the antenna serves with this duplexer as both a receive and transmit antenna. All right, so that's a nice introduction, right? Different frequency bands, kind of gives you kind of the background of why we're studying the things that we're studying. Of course, 5G is big now, and so all of these issues, antenna issues as well as the microwave issues, are important in 5G. So I'm sure some of you will probably ultimately end up working in that area. Or at least I would hope so. Interesting area. All right. So first order of business is microstrip. Right. So let me shift to the notes for that, and you'll be reading the book as we as we go along here, right? It's going to be crucial to read the book carefully in this chapter. Okay, so, right, make it a little bit better orientation of the camera. Okay, so here's a microstrip, right? Ground plane, right? Conductor, uh, dielectric, epsilon relative, right? Of some height, h. And so, what are we really interested in? Well, we want to know for a given material that we purchase with a given dielectric constant, the height would typically be specified when you buy the material at any event. And then the question will be, what width W do we need to use to get a particular characteristic impedance? Okay, so right, the fields are primarily in the dielectric, but there's fringing fields as well. So some of the fields are in the air, right, under a dielectric constant of 1, and some of the fields are in the dielectric substrate, right? And so the effective dielectric constant is not 1, and it's not that of the substrate either. It's something in between, right? So, so the effective dielectric constant is specified here. Okay. So it's just a formula, right? This could be empirically derived, right? Probably is, right? So remember, what's the deal here? E is this way under there, and H is orthogonal to it. Right? Electric and magnetic fields. And so they propagate in and out of the page or down the microstrip line. And so this is a TEM line, right? That's true is provided that you don't excite this structure at too high a frequency, right? Just like a regular waveguide, a rectangular waveguide rather, you'll have other modes that can be excited. So typically, if you stay at above a certain frequency F, right, then the only mode that will propagate on the line is the TEM mode. And under those circumstances, the following equations apply. Okay. All right, so the velocity, right, is speed of light divided by, check that formula real quick, all right. Um, yeah, got to be a little careful there. This should be epsilon relative effective divided by the square root of the relative effective relative permittivity, right? Beta is omega over velocity, right? Waveguide wavelength, or the wavelength of the TEM mode propagating on the line is that in air divided by the square root of epsilon effective. Right? Lambda naught is C over F. Right? Okay, so right, we've got an expression for the effective dielectric constant, right? And so then, right, we have equations that we can now use to get the characteristic impedance, right? So this is what we want to specify typically, 50 ohms, 75 ohms. We'll do an example coming up soon, and then we need to know what the height to width ratio is for a given dielectric constant to achieve that characteristic impedance, right? So we'll solve ultimately for W over H or H over W, reciprocal. Okay, so all of that. So it turns out, right, going the other way, uh, we have two different formulas depending on whether the width to height ratio is less than 2 or greater than 2. You'll see this when you read the text, right? So in the event that W over H is less than 2, then the W over H ratio is given by e to the A over e to the 2A minus 2. And if it's greater than 2, W over H is greater than 2, it's given by this more complex formula. But you can see those formulas in the Okay. I hope this thing is still recording. I think it is. On the page 2, right? So A and B are given by these formulas. So here, if I know the characteristic impedance that I want, again, 50, 75, whatever characteristic impedance we desire, and that depends on circumstances, right? And I know the dielectric constant of my substrate, then then I can compute A and B. Once I know A and B, then I can come back over here and get the W over H ratio to achieve that particular characteristic impedance. Okay, so pretty straightforward, right? All right, so very good. Right, read sections 10.1.1. He's got other types of planar transmission lines, right? This is microstrip. So we've got formulas for microstrip, but very often, right, you'll use some other type, like strip line, conductor, conductor, conductor in the middle, he buried in some epsilon relative, or coplanar waveguide. You see this quite a bit, right? Substrate, uh, width, and spacing here. So coplanar waveguide is used a good bit. And so there'd be some set of equations that one could determine the characteristic impedance of these geometries for. They wouldn't be the same as that for microstrip, but they would be somewhat similar in form, right? You could get those off the web, or there's all sorts of information available for, and there's all kinds of little apps too online that would tell you the width to spacing ratio in order to get a given characteristic impedance for coplanar waveguide with a given epsilon relative, right? And so these concepts are extended fairly straightforwardly. Okay, so probably the best way to proceed at this point is just to do an example, right? That's the best way to digest this material. So this will be a homework problem, and so this at the same time will present the solution to it. So you need to, work through this carefully, and then later on you'll just have to send me an email verifying that you've completed the next set of homework. And so this is the first of those. More to come, right? We'll have a handful of assignments out of chapter 10, and then we'll kind of draw a line in the sand, and you'll send me an email indicating that you've done that, right? And I've got most of you have sent me an email on the previous problem set, right? Here's the list of names that I have. Right now, it's grown to 38. I'm sure that's not everyone. So again, if you haven't given me 14 through 17, you need to let me know that you've digested those concepts and worked through it. Hopefully, you'll see your name in there in the book of life. Okay. So we're going to do this. And you got another homework assignment out there on antennas, and you're supposed to email me on that as well. Right. 14 through 17. All right. I'm waiting to hear from you on 18 through 21. Hopefully, you've worked through those and looked at the solution and digested the solution versus your work and uh, confirmed that the two are reasonably close, right? So that you've got those ideas down. Now we're working on another set, right? This is chapter 10. All right. Right. So let's look at homework number 22, which is problem 1011. So we're just going to work some problems out of the back of chapter 10. Pretty good problems in general. Right. So what's the deal here? Right. Let's find that really quickly. Adverb. All right. What problem are we working? This problem. Right. Here's the picture. 1011. Suppose the microstrip circuit shown in figure 1053 down here is realized atop RT Duroid board of problem 10.8. So you got to go back to 10.8 to get the characteristics of the material, right? This is manufactured by Rogers. they're pretty good about giving you samples if you ever want a sample. And so it's 50 mils thick, right? That's the thickness of the substrate. The dielectric constant is 10.8, right? It gives you some other parameters in here that you can use to compute the loss on there. So I just ask you to read that section. Right? Read the section on loss. There is some attenuation as the wave propagates down the line, and Stu has a little section in there on that. Go ahead and read that. So we're going to use that material in this problem, and here's the problem at hand, right? Suppose the microstrip circuit shown in the figure below, this one, is realized atop that material, assuming the board material is lossless, right? So it's not lossless, but for now we're going to assume that it is. Determine the line width required to get 75 ohm impedance, right? And now that you know that width, right, uh, assume the load is 150 plus J150 at 1 gig, and find the length of these stubs, D through and L stub, in order to match the line to the load, meaning that looking in at this point right here, right, you're going to see the characteristic impedance, or in this case, 75 ohms. Right? So we're dealing with a 75 ohm line, not a 50 ohm. All right, so let's go through that, right? So, right, we need that W over H ratio, right, which is 8 e to the A over e to the 2A quantity, e to the 2A minus 2. Okay, so A is Z naught, right, which is 75 divided by 60, and then I just fill in the formula, right? Fill in the formula. A is given up here, right? We know that needs to be 75. We know the dielectric constant of the substrate. Just fill in the formula and get A. Okay, so now that we know A, right, 3.2357, we know that W over H is 8e to the A divided by quantity e to the 2A minus 2. That gives us 0.3156. That's less than 2. And so this is the right formula to use. This is the correct formula to use. So that gives us a width, right? That's the strip width, right, of 0.3156 times H, right? And he told us the material had a 50 mil thickness, right? So that means that the width of the strip needs to be, 15.78 mils, or almost 16 mils. Okay, so now we know how wide to make the strip, right? Back up here, we know how wide to make the strip in order to make this thing have a 75 ohm characteristic impedance. We know epsilon relative, and we were given H because we bought the material, right? When we bought the material from the manufacturer, we purchased a given height and a given epsilon relative, and this was clad with metal here and clad with metal there, and then we etched away everything but the strip that we needed, creating a 75 ohm transmission line. All right, so we got part of the problem done. Right now we know the width. Page 3, moving to that page. Right. So now it's back to matching. Remember matching from Fields 1, right? How do you do that? You use a Smith chart. That's how you do it. So here's our load, 150 plus J150. Z naught everywhere on the line is 75. We made it that way because we cut the script width appropriately. So we need these two numbers, D through and L stub. Now this is an open circuited stub. If it were a short circuited stub, you would drill a hole and solder this to the substrate. But this is open circuited. Okay, so little z load, right? First order business. First order business is to get to little z load. It's not very bright. So little z load is the honest to goodness load divided by the characteristic impedance, right? So 75 will go in 152, 150, so 2 plus J2. So plot that on the Smith chart. So let's do that real quick. Here's the Smith chart. You've seen these before, right? Ugly little things, aren't they? Not really. They're beautiful. Okay, so 2 plus J2. 2, there's your 2 circle. R equals 2 circle. There's your 2 reactance circle. The intersection of those is Z load. There's Z load, right? Now, remember in this problem, we've got things that are being put in parallel, right? This stub is in parallel with a line, not in series. So we need to work in admittance coordinates. Remember that, right? So Z load, if I want to know the load admittance, how do I do that? I draw this line and I go directly across the chart. So this is Y load. This is Z load, 2 plus J2, directly across the chart, whatever this is. I could read off the G and B circle, right? Use the right language. That would be Y load. So then I draw my circle, right? So-called SWR circle, gamma circle, solution circle. It's got a bunch of names, but that's it. I'll try to darken these lines up. I should have. Bear with me and I can do it now. Should have thought about that earlier. Give you an opportunity to pause and reflect. Well, kind of ugly, done quickly. Okay, Z load, Y load, right? So here I am. Being right here is the same as being at the load, right? At the load admittance. I'm at the load admittance. Don't lose track of that. Your position on the Smith chart and your position on this circuit diagram have to be in your mind at the same time, right? So we move from Y load toward the generator, right? So that's monitoring the input admittances as I move this way. Where do I stop? I stop where Yn is 1, right? Plus J 1.6, right? So if I could only get rid of the plus J 1.6, I'd be finished, right? And so how do I get rid of the plus J 1.6? I put this stub in parallel with the line, and I want to make sure looking into that stub is minus J 1.6, right? Because 1 plus J 1.6 minus J 1.6 is 1. So then Y in here, little y in here is 1. So little z in there, z in at that point is 1 over 1, which is still 1. And so honest to goodness, big Z in there is 1 times Z naught, or 1 times 75, which is 75. So as far as this line's concerned, it sees 75 ohms and there's no reflections. That's the whole intent here, right? Remind yourself of what you're doing, why you're doing what you're doing. Okay, so, right, here I am, Z load, Y load, I stop here. So that gives me this distance D through, right? Well, how long is D through? It's from here all the way to here, right? So read that off. That's 0.042, that's this much. Add to that 0.172468. Okay. So where am I? 3. Yeah, there it is in the notes. 0.178 plus 0.042. Right. Make sure you get that. 0.172468. That's this much, and I got to add 0.01234, 0.042 to it. right? That's what I'm doing. So that is 0.22 lambda for D through. Okay. Now, right now I need to figure out how long this stub needs to be so that looking into it is minus J1.6. Where is minus J1.6? It's right here. Okay, it's right there at that location. The SWR circle for the open circuited stub is the periphery of the chart, right? Is the periphery of the chart. So it's a new Smith chart problem, essentially. So if I'm right here, that is an open circuit, or that's a Z load of infinity, or a Y load equal to 0, right? Reciprocal. So I need to work in admittance because I'm putting things in parallel. So being right here is the same as being right at this point right here. Right there, right? So then I move, then now I'm moving toward the generator, right? And I'm going to stop where I get minus J1.6. So how far is that? Well, it's a quarter wavelength plus this much distance. So it's a quarter wavelength plus 0.34 minus 0.25. So 3.34 minus 0.25, I got 0.09, and we're going to talk about this first sloppy solution, which is in error, right? We're going to see why I made these errors. Sometimes it's important to make mistakes and then figure out why those mistakes were made, and that gives you some cautionary tales, right? So that you can be a little more conscientious and avoid those mistakes, right? So I thought my stub was this long, but that's not right. It's that long plus a quarter wavelength, right? Because I had to start over here. I was just got in a hurry and started from here, which was not correct. Right? Why is that not correct? This is an open circuit. Z load is infinity, so Y load is 0. Where does 0 occur on this on the periphery of the chart? It occurs right here. And so I have to measure from that. Okay. So let's see the errors that I made. I got the right distance for D through, right? It's 0.22 lambda, but then I turned around and multiplied it by lambda naught, right? At 1 gig, the wavelength in air is 30 centimeters. I divided it by epsilon relative, which is 10.8. That's wrong. Why? Because I needed to divide by epsilon relative effective, right? Some of the field's in the air and some of the field is in the substrate. This is just a substrate's dielectric constant. So I made a mistake there, right? And then when I computed, so this is wrong. Why? The not because this is wrong, but because I got the wrong wavelength, right? So this is an error. So the professor screwed up. Now L stub, right? This length, the mistake I made there was not only to use the wrong wavelength, right? Because of the epsilon relative, I multiplied by 0.09, right? Not, which is just this distance, not 0.09 plus 0.25. So this is riddled with errors, right? Mistakes that one can make if you don't pay attention. So let's try again, right? Let's revisit this. First, we need a epsilon effective, right? So we got to go back to the formula and use epsilon relative and the width to height ratio to determine epsilon effective, right? You can see that that's 7.088, not 10.8 that we said earlier, right? Not the 10.8. It should have been 7.088. So lambda guide, or lambda, is going to be lambda naught divided by the square root of epsilon effective, which is 30, right? In free space, uh, the wavelength is 30 centimeters, right? I need to divide by the square root of epsilon, not epsilon. So 7.088. That gives me an 11.268 centimeter guide wavelength, or the wavelength of the wave propagating down the line. So now my D through is 0.22 times 11.268, or 2.479, or about 2.5 centimeters, right? And then L stub is, in D, it's 0.34 minus 0.25 plus 0.25 times lambda G, or 0.34 lambda guide, which is about 3.9 centimeters, right? So these are Stu's answers from the back of the book. So finally, we get those to agree with the solution. Okay, so right, made a few mistakes, right? We having to revisit Smith charts, remember all the Smith chart stuff, right? Remember the Smith chart material is very important, right? So now we were able to, right, figure out, right, how long D through and L stub needed to be, so that looking into the line at this point is 75 ohms. Okay, so I'll load these up on the engineering FTP for you. Hopefully these notes will be of some value to you. Right? Go back and figure out how the professor messed up. Right? That's a good example of somebody that's not paying attention and made a few mistakes. See, pay attention to the mistakes that I made so that you don't make them. And then here's the corrected version. Right? So that'll be something fun to do. And then I'm going to load these up on the engineering FTP site, and the notes as well as the video. So hopefully that'll be of some use to you. Then we'll move on, right? What's the next section? More homework, a little more video stuff, and some notes. The next section is on, S parameters. Yeah. So next order of business is scattering parameters. Very important, right? It's how you characterize a microwave network, right? So you need to go ahead and do some pre-reading there. Go ahead and read those so that when we go through it, and we'll work a bunch of examples, it'll be you can digest those ideas, and then we're just chopping our way through this material, right? So we're going to get through 10 here, a bunch of sections in here, but they're interesting, and we'll knock this out. And again, the plan, I think, is to put the antenna material and the chapter 10 material on the final. That's kind of where that's my thinking now. If somebody doesn't like that, they can email me and complain. Maybe I'll change my mind. Probably not, because I want to cut down on the amount of right. I want to cut down on the amount of stuff I'm printing out and grading and scanning and sending back to you. That's a nuisance. So under these special times, we want to minimize uh, the amount of that kind of thing, back and forth, back and forth. Right? If we were in normal classroom, it'd be straightforward. Right? But we're not in those circumstances, so we need to adjust. But that said, we're going to push through this and get it done. All right, very good. Have a good day. Hope everybody's well. You know, we'll get through this. No big deal. Just do it.